together. So we had 1 plus 6 was 7, and then plus another 6 would be 13, plus 12 would be 25. Whoa! 32. Yes.
Are you swiveling?
Yeah. Every day I'm swiveling. Okay, so I had 32 wins out of 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 32, well, that's easy, right? 32 out of 100. So what is our probability of winning this game? How should we express this? So here is 32 out of 100 is 0.32 is 32%. Don't give me naked answers. Naked answers are things that you don't convert to a decimal and percent. It's easy when it's 32 out of 100 for someone, I don't want to say easy, but it's easy to see what that means. Oh, that's 32%. Well, but if you had like 17 out of 54, is that good? That's why we convert it here and here. But we leave this because we need to know the number of trials. So we don't reduce it. We want to have that to leave it as the number of trials. In probability, there's something called a tree diagram. It helps us assess the probability. And our goal, remember, our goal in this chapter is to say, here's what should have happened. Here's what did happen. Is there a gap? Like, is it weird? Was my result abnormal? My question is this abnormal? Well, based on our data, does it appear to be abnormal? It appears to be abnormal, but we don't know. So this is called a tree diagram. And basically what a tree diagram is, it allows us to follow all of the lines of logic. So you ready here? We start out, we are playing the ace game. The first card is an ace, the first card is a king. What goes here is the probability that that happens. We had 5 cards. What's the probability that the first card was an ace?
2 out of 5.
So 2/5 goes in the box. Down here, first card, king. What does it equal? 3/5. What do you notice about those two numbers? Does that make sense? Why does that make sense? Articulate that. It's all the options. There's nothing else. So these 2 boxes comprise everything that could possibly happen. If they don't add up to 1, what happened? One of 2 things. You're missing something. So either you didn't calculate your probability right, or you're missing one of the options. Try to fill these in. Okay, thank you. We'll take care of it. Thanks, Cam. Appreciate it. Bye-bye.
You said the test was Friday or what?
It's going to be next Friday. It's the 49-minute class periods. All right, so let's check out why is the tree diagram useful. It's sort of useful in this way, but really back here are the outcomes. So this is kind of midway. This is halfway. This is where we're going to make the money. This is where you're going to find some real results. You're going to find some probabilities here. This is how it works. Ace game. First card is an ace. Second card is an ace. Is that a win or a loss? That's a win. So label this one win.
Can you explain why it's fourths?
Yes, because one of the cards is known. So how many options do you have left? So as soon as you pick up a card, your probability of getting another ace, there's not 2 aces left, there's only 1. And there's only 4 cards to pick from. You follow? So imagine, I've got these 5 cards. All right. I pick up one of them. Ooh, an ace. How perfect. Now, I followed this line. So here I am. But now, my options, how many options do I have? I don't replace it, so I only have 4. How many of them would cause me to win? I need an ace.
What's the thing after that?
Hold on 1 second. What? So this is how it works, right? So I pick this out and I get a king. Well, how many kings are in this pile? 3. So 3 of them are going to be the king option. 1 of them is an ace. look here again. What do our probabilities add up to? 1/4 plus 3/4. 4/4 is 1. What about here? 4/4 is 1. So our probability in our tree, it always needs to add up to 1. So then when we go here, so this is a win. So we're really asking, what's the probability that the first card is an ace and the second card is an ace? This is how it works. Use your finger to trace with me. You ready? We started the game. We got an ace, then we got another ace. So probability that the first card is an ace and the second card is an ace. This, and we're multiplying. 2/5 times 1/4. And means multiply in probability. So this has to happen and this has to happen. And means multiply. It's not logic, it's do. Pick a card. Nah. Before you start, how many cards do I have? So no matter which way it goes, my probability was 5. How many aces are there? 2. So there's a 2/5 probability you're going to get an ace. 3/5 you're going to get a king. Okay, do it. Before you do this, don't put it back in. Okay. All right, what'd you get? Okay, perfect. Now we got a king, so put it on the table. These events right here, the probability of this one depends on that one, right? Because now I don't have 5 cards here. I only have 4. So there was a 3/5 probability that happened. There's a 60% chance you were going to pull a king. Fine, perfect. Now, you're going to go back to the pile. Yes?
So is it different if you pull an ace and a king? Is it different if you pull the ace before the king or no?
That's what this tree diagram shows us.
It's not.
When you start out, you've got a 2/5 probability of pulling an ace, a 3/5 probability of pulling a king. A tree diagram shows you the probability of every possible outcome. So now, we're down here right now. You are right here. Your first card was a king. Ooh, what's the odds that you win? That's the question you're asking. What's the odds that you win? What could you pull out of here that would cause you to win? Another king. How many kings are in here?
2.
Out of how many cards? How many ways are there for you to lose? Are you guys with this? Are you tracking this? So there's 2 out of 4 of the ways I win, 2 out of the 4 ways I lose. Pull one out. Hope you're hungry. Because it's winter, chicken dinner. Okay, that was a roundabout way to say it, but this is the tree diagram. And so we're going to follow all the logical ends. This is not do. This is theory. So understand in your head probability, there's something you do, what you just did. That was this over here. We did this. A tree diagram is the theory of what could happen. What could happen? And that's why I made that big point to say it adds up to 1. It adds up to 1. It adds up to 1. It has to add up to 1 because it's everything that could possibly happen. And the beauty of it is you make this tree diagram and then I say, hey, Madison, what was the probability that you got an ace and then a king? And you can tell me because the tree diagram takes into account that line of logic. So when I follow this, I'm going to multiply the probabilities of each step. So 2/5 times 3/4 would be 6/20. What is that as a percent? 0.3. This is a loss. There's a 10% chance that you win by drawing an ace first. But there's a 30% chance that you lose. But Mr. Saris, those don't add up to 100. You're right, because those aren't all the outcomes. Add to 1, add to 1. Guess what's going to happen right here? All of these are going to add to 1. At every step, all of the outcomes are represented. Follow these lines of logic here. Apologies. What'd you get?
They're all 30%.
Notice my clothed answers, meaning I don't have any naked answers here. So 3/5, 2/4, 6/20, 0.3. Down here I've got 6/20 equal to 0.3. Bless you. What is the least likely thing to have happen?
Win by 2 aces.
Win by 2 aces. What is the most likely thing to have happen?
Any of the other options.
Any of the other options. So either lose or win by kings. Does that surprise you? So what about our results? This is the theory. So what about our results? Are our results weird? Is it weird that we had 32% wins? So tell me, what's the probability of winning?
0.4. Yeah, 0.4.
You
Exactly.
add, right? Because it's or.
Yes. When we say find the theoretical probability of winning, we have to determine that for this context. Here's the context right here. Think about yourself, and this is the hardest part for people studying probability. You have to visualize yourself doing this activity. Because they're going to ask you find the theoretical probability of winning the game, and people are like, well, I don't know what to add. You got to put yourself in the game and think, well, what would it take to win? That means it's the probability of 2 aces or 2 kings. Not to be confused with 2 princes, spin doctors. You guys familiar with that? Or did the joke not land? Bummer.
Wait,
I
what
tell
was
that one every year. I said, not to be confused with 2 princes, but the spin doctors. But if you don't know what that is, then it's music jokes are tough because there was a period of time when it was like, no one knows music because you can't get old music, but now you can. So 2 aces or 2 kings. And it's or, so as Annie pointed out, it's adding. So I'm going to go 0.1 plus 0.3 is equal to 0.4. Good rule of thumb, you should have this entire mathematical equation as your answer. It lets me know you didn't just pull this out of nowhere. This is what you added.
If you added the fractions instead, is that okay?
It's okay.
Do you need to include the P of 2 aces over 2 kings in this?
You should show that.
Is the or the U upside down?
It's the union. Onion. So, that's great. Before you play the game, you sit there and you're like, okay, I've made my tree diagram. I know what it's possible to win. I only have a 40% chance of winning. So was our result weird? It's close. It's definitely not way out of the ballpark, right? We'll evaluate later this year. What does it mean? Like, how close do we have to be? But for now, we're sort of close. What about this person?
We're out there.
Lucky, right?
The 1 is the same distance away as the second.
Aha! Isn't that interesting?
Oh.
This one is off by itself. Man, is it crazy. Is this one equally crazy? Yeah, so check that out. See, so that's the kind of thinking you have to have. You have to look at the whole problem. You have to say, yeah, there's only one here, but there's also only one here. Sometimes this can be distracting. Oh, it's by the others. Well, yeah, but it's equal distance apart. So we'll talk about that later. But the thing is, we want to be able to do not just from the beginning the probability, but in the middle. So what's the probability that the first card was a king, given that the person won the game? So now we have to be retrospective. We have to look back. So the person won. What's the probability that the first card was a king? Let's write it out. P what? P, first card, king. Then what? What does this mean?
What is it?
Like, how do we make this into numbers?
Doesn't the king have to be on the bottom? Is the winner?
Yeah, the 0.4.
Given that the person won. So that's going to be the bottom.
point four for what the game.
So on the bottom goes 0.4? Yes.
And then you had a 3/5
Point to getting
So like 0.6
Wait.
over 0.4. That's
a.
not.
What? But wait, they can only. Oh wait.
I love this.
So the, given that the person won,
So did they have to win by a king?
What's the
With
only way to win? This
with
is the
the
question.
first
So the
Oh,
temptation here is to say,
probabilities
I
are-
understand that 0.4 was my probability of winning. And so then I zoom all the way back to the beginning and I say, oh, the probability that the first card was a king was 3 out of 5. That's not true. This is conditional.
Yeah,
So in order for them to have fulfilled this condition,
it's 0.3.
was it 3/5?
No.
It's got to be from the other branch because the other branch is saying the first card was a king, but we won.
Oh.
Right.
so first and second card is king, so it's
I had it.
0.3 over 0.4.
So sometimes you have to put yourself. So sometimes you have to put yourself in these shoes, right? Given that I won, what's the probability the first card was a king? What would it mean to win and have the first card as a king? It would mean the second card as a king. So you have to put that 0.3 up top because don't overthink it.
What's the point?
Are you gonna ask questions like that?
Oh, out
Yes.
of all of the.
Without the diagram.
You're gonna have to make the diagram.
I know, but like, are we gonna have questions like that? Like, we don't have a diagram at all.
Yeah,
So point
very
4 is-
regularly.
Point 4 is the
Yeah, I
chance.
know they like die.
0.4 is the chance that they actually won.
Is the chance of winning it all, and point 3 is the chance of winning by having the first card as a king. Okay.
So first card as a king is 0.3, given that you won. Let's zoom over to the check your understanding. I'd like for you to spend a little bit of time trying that. This is Lexi's point. Lexi said, are we ever not going to have a diagram? Welcome to not diagram. You have a problem, and you're going to need to draw the diagram and then be able to not only follow the branches to determine conditional probability, but also pull out some conditions within there. So work in your groups on the check your understanding, and then we're going to pop back over to the notes here in just a minute. So, like I said, sometimes the hardest part about doing a probability problem is imagining, like, what is the problem saying? You have all these computers. They are from one of two places. Boom, branch. When you go to those places, 3 things are happening at each of the places. Laptop, computer, tablet. Finding the probability of those things is kind of the trick. Talk to me about Texas and California. I'm going to switch these because I switched them in my notes. I'm going to put California on top. Alphabetical order. Not necessary. Probability of being from California. 40%. You can put 0.4. What about from Texas? Mental check. Add up to 1? Yes. So then out of California, probability that it's a desktop. 0.25. Probability laptop. 0.3. Probability tablet. Mental check. Add up to 1. So all of the scenarios when you get to California should add up to 1. This is everything coming out of California has to add up to 100. So now everything coming out of Texas, what's the probability of desktop? Because we're advanced. Hooah. What else? 0.2. What about tablet? So now, check. Add up to 1? Indeed. Now is when the conditions start. What's the probability that your computer was from California and was a desktop? 0.25 times 0.4 is 0.1. Probability that it's from California and it's a laptop. And means multiply. So from California and a laptop. 0.4 times 0.3 is from probability that it's from California and a tablet. 0.4 times 0.45 is 0.18. Yes. Mental check. Do these add up to 1?
No.
Should they?
Add up to 0.4 because that's what they should have.
Ah, yes. At the very end of the branches, we are evaluating not the entirety of the outcomes. All of these should add up to 0.4. And they do. Probability desktop and from Texas. What'd you get? 0.06. Probability from Texas and a laptop. Point who? Probability from Texas and tablet. What is the greatest likelihood? Like what is the thing that's the most probable out of anything? Having a tablet from Texas. Do all of those add up to 1? Check your math. Does everything add up to 1? So this was 0.4 and this is 0.6. So 0.6 plus 0.4 equals 1. You have a total of 1. Every possible outcome represented. So now find the probability that the computer is a tablet, which would mean the probability that it's a tablet. So here's what I do when I get a problem like this, right? I look at the beginning. Do they measure tablet first? No, they measured state first, which is fine. But sometimes I'll say, what's the probability that it's from Texas? 0.6, right? So what does it mean to have a probability of it being a tablet? That's the probability of a Texas tablet plus the probability of a California tablet, right? What are the two numbers that go into that? Where do I find that information? On the branches, right? So Texas tablets plus California tablets, 0.42 plus 0.18 is equal to 0.6.
Why did you subtract tablets?
I didn't.
Oh.
A Texas tablet, California tablet. Yes.
So if this was like on the test, we have to write that probability formula.
This is acceptable. This is preferred.
What's acceptable?
Just this.
Oh, just the bottom. Okay.
Probability of tablet is 0.42 plus 0.18. That is okay. Equals 0.6. Don't give just 0.6. Give the addition problem.
Don't you have to have like a fraction or decimal percent?
If given as a fraction decimal, it's fraction decimal and percent. What you've been operating as. So ideally, the decimal is what it is. Because remember, our probability chart, our probability model, all outcomes represented adds up to 1, is a decimal between 0 and 1. Decimal is the preferred form of probability. So if they give you a fraction, you need to have decimal. If they give you a percent, which they did, you should have decimal. A good rule of thumb is to say, if I have a fraction, then I put the decimal, then I put the percent. But at the very least, you need to have the decimal. I'm just trying to train your brain to think about it in terms of, it's not, you don't want to say there's a 25% chance. You want to say there's a 0.25 chance. If we select 4 computers at random from the distribution center with replacement, what does replacement mean?
You like put it back.
You put them back. In our model with the cards, it would be as if Lexi, and I don't want to mess up your thinking about this, but pull a card. What'd you get? The king. Okay, now, so in the second pull, the denominator would be 5. So with replacement means you put it back. So it protects us against having to change the denominator every time. If we don't change the denominator every time, so you had a fun insight on this one. What is another way to say the probability of at least 1? The probability of at least 1 is equal to 1 minus the probability of none.
if it wasn't one, would you still have none? Like if you had like the probability of at least two, would it be like
So
minus-
let's say we had the probability of at least 2. It would be 1 minus the probability of 1 or 2.
So if it was like 9, it'd be like anything below 9. Probability of like 9 minus p, anything below 9.
Yeah, so a common example of this is, what is the probability of rolling when you roll 2 die at the same time? What's the probability of rolling a number less than 12?
All of them except for getting a 6.
All of them except getting double sixes. So instead of counting the ways to get 2 and 3 and 4 and 5 and say all the way up to 12, you'd say, oh, well, there's only one way that it doesn't fit. That would be 12. So, 35 out of 36. Does that make sense? So what's the probability of rolling something less than 11 on dice? 2 dice.
35. No. 33.
33. Because that would be like saying the probability of 1 plus 2 plus 3 plus 1. Or, well, 12 is 6 and 6. And 11 would be 6 and 5 or 5 and 6. So there's only 3 ways to get, so it's 1 minus the complementary event. Yep.
In those situations, if you got like a 1 and a 1, that counts as 2, right? Because it's like, you could get the first dice as 1, the second dice as 1, or you can get the second dice as 1, the first dice as 1. Like, are those 2 events, or like 2 possibilities, or 1?
Yeah, that's kind of confusing. So let's say I had a red die and a green die. So a common way that we model this would be with a chart, and we'd have the red one up here and the green down here. If I roll the die and the red one is green, the red one is 6 and the green one is 6, what's the difference between rolling it and getting the green one is 6 and the red one is 6? Is there a difference? No. There is a difference, however. Let's make it black and blue because those are the colors that I have. There's no difference here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There's no difference here or flipping them. There is a difference here, though. And that make sense?
Yeah, but why?
Because this is 2 distinct outcomes. This is 1 outcome. I'm saying to get a 12, it's a 6 on both of them. So it's the same outcome. This is a different outcome because literally the dice is different. There are 2 ways to get 11. A black 6 and a blue 5, or a black 5 and a blue 6. There are 2 different ways for that to happen.
Yeah, I get that, but like, there's like, wouldn't you roll like a black 6 and then a blue 6, or a blue 6 and then a black 6? That's like 2 off. You know what I mean?
No, because black 6, blue 6 is the same as blue 6, black 6.
Okay.
Be the same for like if you were trying to get a 6 and you got 2 3s.
Yeah.
Yes.
Blue 3 and black
Yes.
3. Okay.
So why is that 5 on the blue on the bottom?
Because this would be a total of 12, this would be a total of 11, this would be a total of 11. There's 3 ways to get 11 and a 12. Let me help you. Can I help? 1, 2, 3, 4, 5. 1. All right, so check this out. It's easy to see it when it's modeled like this. 1, 2, 3, 4, 5, 6. Let's let these be the outcomes of the blue die. Let's let these be the outcomes of the black die. Don't disrespect my boxes. They're people too. So, in this one, we'd have a 1 and a 1. It's okay. It's worth it. Totally worth it. 1, 1, 1, 1, 1. 2, 2, 2, 2, 2. What's that? I don't know.
Oh, on the left side of the road, would it be 5?
Like that? Okay. Notice what happens. So if you track the chart, look at my doubles. My doubles are down the middle. So for example, 11, blue 5, black 6, blue 6, black 5. 2 ways to do it. But 12, there's only one because reversing them is the same. It's a black 6 and a blue 5, like either way you slice it. It doesn't matter where the die sits. It's about the die being that particular number.
Okay.
So when I do this chart, here's my 1-6 combos. So it's blue, black, but
Yeah,
it depends on which die is which.
Okay.
So that's why, so these probability models, such as a tree diagram, such as a chart, can help us see where are the outcomes, where are the overlaps. How do you write what? So when we have something along these lines where it says at least one, it's a probability of none being a tablet. What would that look like mathematically? 1 minus, we pick 4 of them out. What's the probability of none tablet? It would mean the first is not, and what happens then? The second is not, and the third is not, and fourth is not. The word and means or is plus, and is multiply. So now you go to your chart. It's a little, it's dense up here. Let's put it like that. There's a lot of things. What is the probability that it's not a tablet? Say it again. Why is it 0.4? The probability that it's a tablet is 0.6. So the probability that it's not a tablet would be desktop plus laptop from California, desktop plus laptop from Texas, which would mean this is 1 minus the probability that it's not a tablet, 0.4, the first time, times the probability that it's not a tablet the second time, times the probability that it's not a tablet the third time, times the probability that it's not a tablet the fourth time. A shorthand way to write this would be 1 minus 0.4 to the fourth power. Which is 1 minus 0.1296, which is equal to 0.8704.
I got point. Well, yeah, that's what I got when I did the whole thing. But if it's just.
You can't do the whole thing because it'll do, so do 0.4 to the fourth,
Yeah, I got.
Yeah, and then 1 minus.
and then 1 minus that answer.
Yeah, we got point 0.0296 instead of 0.196.
Yeah.
0.0296?
Yeah, when you like.
Because 12 times 12 is 256. The 16 times 16.
I think
So then, oh, I see what you're saying. So what'd you get as your, so this is 0296?
The 1
Five,
minus
six.
0.
No, what?
0.0256.
5, 6.
That's the final answer.
No, you
No,
subtract
it one minus.
That's 1 minus that, which is,
0.9744.
honestly, this is going to be the hardest part. You're going to get this piece, you're going to get this piece, and then they're going to ask you a question where you're like, there's so many conditions. What do I multiply? What do I add? And you've got to think through logically, what would it mean for this to happen? What would have to happen for this to happen? What would have to happen for me to have at least one? 1 minus the probability of none. Okay, what's the probability of none? What would that mean? Well, that would mean the probability that I pick one that's not, and then one that's not. And so breaking this down to where you can get a mathematical equation, honest to goodness, is going to be the hardest part. This is where people get this first, and eventually they're like, oh, I feel super comfortable, I'm good, and then they're like, lost. The best advice that I can give you is do lots of problems, break it down into steps. Take each step as what would have to happen and what is the probability of that step happening. Break it down piece by piece.
Wait, so 0.4, you got that number by.
Can we pop back up to the box and put a little bow on it? You already have all the information in this box. I just want to review.
Dude, what was 4?
Sorry?
Yeah, what was 4?
Multiplication rule is what it's called. The multiplication rule says this: the probability of A and B is equal to the probability of A times the probability of B, given that A.
Is the upside down rule, is that?
And. Think about like when people abbreviate and as like the apostrophe N.
That looks like an
It looks like an A.
because it looks like it spells and. It looks like the N.
And.
And then the slash is given.
Yes. What's that? Do what? Oh, I want to make sure we wrap this up, then we'll talk about 4 in just a second here. And we're going to talk about this in just a second. This is what we were doing when we were talking about the branches of the tree. So the probability of B would be like probability of B given that A. So if something happens, then it would be like that case where we multiply just the straight up probability. So the probability of A times probability of B. We follow the branches of that tree. So this happened, probability of ace, then probability of a king. You multiply down the lines of the tree. Like Anika pointed out, the probability of at least one would be 1 minus the probability of none. And just a quick review of our tree diagram. We've got our branches. Our branches split off to begin with to A and the complement of A, as in ace or king. On the line goes the probability of that given event. Then as we split off, we get the probability of B here, and this would be like C, this would be like D. On the line go the probability.
The complement probability.
Here,
No, like,
down here.
yeah, it's
So here's the tricky part. Let's say this leads to B, C, D. This is the laptop problem, right? This would then be the probability of B, but it's the probability given that A complement happened. So that was like where it's, yes, the probability of B, but it's given that A happened or B happened, meaning the probability that you got a desktop given that it was from Texas. So in the problem, it outlined that probability where it said, of the computers made in California, 25% are desktops. So that 25 goes here because it's subject to having been a part of the California totals. So then on this line goes the probability of A times the probability of B. And that's what I was attempting to articulate to you when we're talking about this stuff over here. These events, so probability of A and B is the probability of A times the probability of B given that A. That's this right here. You follow this logic because this one down here is also the probability of B, but in this case, it would be the probability of the complement of A because this is where probability of the complement of A comes in. Does that make sense? And I'm telling you what's going to happen is you're going to be like, yeah, that makes total sense. And then you're going to sit with your book on Sunday afternoon and you're going to be like,
Sunday afternoon.
so my recommendation would be to try to touch this, meaning work on it a little bit in the meantime before then. Yes?
what if like I know we have the formula if they're dependent, I mean if they're if they're dependent or independent, but if you're like how do you do a tree diagram for dependent outcomes?
We did that with ace and king
Oh, okay.
because the denominator changed. So as soon as the denominator changed, that it was dependent, like the probability of the second event depended on the probability of the first event, meaning we pulled out a card, so now we have 4 in our denominator.
Okay.
So that's why if A and B are independent, then we get strictly this is true. So straight up. Let's talk about number 4 real quick. I know we got like 26 seconds. Not even. This, given that a tablet computer is selected, what's the probability that it was made in California? So given that a tablet is selected, what's the probability that it was made in California? What's the probability that it was a tablet?
0.6.
0.6. And then what's our percentage of California tablets? California tablets? 0.18.
Wait. That's not right.
Is it the answer?
Yep.
6 times 18 is.
It'd be 10 times 18, so it'd be 180 over 6.
Oh, it's over. Okay.
Yep. Alrighty. More than ever. Oh, I need to give you homework. I'm so sorry. More than ever, if you have questions,